This is polyclear crater. And you can see arrows pointing to some faded streaks flowing out of the crater wall. This is in a slightly different location in the southern hemisphere of Mars. At this location, actually, we have multiple observations from different times. However, we see the hydrated salts only when these streaks are thickest. At other times, when the streaks are narrow and short, we do not see any evidence of hydration. This, again, just like Horowitz, means that the source of hydration, or the source of molecular water in the crystal structure of the salt, is either due to the presence of RSL or some other processes that created RSL. Regardless, again, just like Horowitz, the presence of hydrated salts in its flow means that these features are forming due to contemporary liquid water. If we go to the next slide, the presence of perchlorate also has some other big implications for water on Mars. You can see the pure water stability on Earth. For example, if you take a glass of liquid water here on Earth, the water will remain in the liquid form until you hit 0 degrees Celsius, when it will start turning into ice. If the temperature approaches about 100 degrees Celsius, then that cup of liquid water will start boiling, and most of the water will start going into the vapor. Next, if we take the same glass of water to the surface of Mars, similar thing will happen. The water will freeze at 0 degrees Celsius, but because of the thin atmosphere of Mars, the water will start boiling as soon as the temperature reaches close to 10 degrees Celsius. Therefore, pure liquid water is highly unstable on the surface of Mars, and this is where perchlorate can help us. Next, consider a water mixed with perchlorate or perchlorate brine. If that happens, then the stability of that salty liquid water on the surface of Mars vastly increases. As you can see in the graphic, the perchlorate brine will remain in a liquid form until we hit negative 70 degrees Celsius, and will not start boiling until it is 24 degrees Celsius. Therefore, the presence of perchlorate vastly increases the stability of liquid water on the surface of Mars. Perchlorate also has one other huge implication for water on Mars, and for that I'm going to turn it to Mary Beth to explain that.
And thank you, gentlemen, and we will now hear from Mary Beth Wilhelm. We'll go to the West Coast at the Ames Research Center. Mary Beth.
Thanks, Dwayne, and thanks, Luzu. So Luzu discussed the first major implication of our work, which pertains to the increased stability of liquid water on the surface of Mars. I will now discuss the second major implication and then discuss some of the broader significance of our findings. So perchlorate salts have a special capability pertaining to the absorption of atmospheric water through a process called deliquescence. Basically, if the humidity in the Martian atmosphere gets high enough, perchlorate salts will absorb the atmospheric water until the salt dissolves and forms a liquid solution. This is one possibility for explaining the formation of RSL. So this sort of physical process can explain the features that we observed here. The discrete darker patches observed in this image may be formed by deliquescence. It is also possible that the formation of RSL is due to other types of processes in which we won't go into depth on here. Perchlorates have a much higher ability to dissolve in water compared with other salts that we see at the Martian surface. So our observations could also be explained by some other liquid water source dissolving perchlorates that are naturally present in the soil and then later depositing them as a solid in higher concentrations. But again, deliquescence is our favorite scenario. So here you see a map of the distribution of perchlorates on Mars. The red triangles indicate places on the surface where perchlorates have previously been detected by rovers or landers. Perchlorate is suspected to be present at both of the Viking landing sites and was found in the northern plains by the Phoenix mission in the late 2000s. Most recently, it was detected at Gale Crater by the Sample Analysis at Mars instrument aboard the Curiosity rover. Our detection of perchlorates at RSL sites are shown here in blue, are the first to be made using data acquired by an orbiter. We have increased the number of known locations of this important resource on the Martian surface, showing that perchlorates are perhaps more widely distributed than previously thought. So to summarize, our findings strongly suggest that these recurring slope lineae are formed by liquid water on present-day Mars. The spectroscopic detection of hydrated perchlorates indicates that this water is briny and not pure. So with that, I'll now discuss some of the broader significance of our findings. So water, as I'm sure many of you have heard us say on multiple occasions, is an essential ingredient for life. Our results may point to more habitable conditions on the near surface of Mars than previously thought. Here, potential habitability by Earth-like microbes is unclear. To assess habitability, we would first need to determine how cold and how concentrated the brine is. But the detection that we've described warrants further astrobiological characterization and exploration of these unique regions on Mars. Finally, water may be an important resource for future human explorers and inhabitants of Mars, and may decrease the cost and increase the resilience of human activity on the red planet. Looking forward, it is imperative for us to further understand the source of these water for these features, as well as the amount. And with that, I'll turn it back over to you, Dwayne, at NASA headquarters.
Thank you, Mary Beth. Okay, ladies and gentlemen, we now will transition to our question and answer. We have a lot of media, not only here in Washington, but on the phone lines, and we want to get to social media. So I'm going to ask you wait for the mic. Please limit your question to one. We'll try to get to as many questions. Our participants will be here following the press conference, but we have a gentleman here. If we can get a mic here. And your name and affiliation, please.
I'm Chip Reed. I'm Chip Reed with CBS News, and I'd like to try to pin you down, given all this new evidence. How likely do you think it is, a 1 to 10 point scale or whatever you choose, that today there is some form of life on Mars?
Okay, I guess everybody's looking at me, so I'll give you my feeling. You know, when you look at Earth, water is an essential ingredient, and just about, well, not just about, everywhere we go where there's liquid water, whether it's deep in the Earth or in the arid regions, we find life. This is tremendously exciting. We haven't been able to answer the question, does life exist beyond Earth? But following the water is a critical element of that. We now have, I think, great opportunities to be in the right locations on Mars to thoroughly investigate that. And I think the reoccurring slope lineae with the actual water on the surface allows us, with surface mobility that we have in our assets now and in the future, to be able to go over to thoroughly investigate that and indeed look for life and then make that positive identification.
Go ahead, John.
Yeah.
I'm sorry.
Yeah, I just think the really exciting thing about this is that our view of Mars, of this ancient Mars, and the possibility of life originating on Mars, has been really about seeking chemical fossils of possible past life on Mars. The existence of liquid water, even if it's super salty, briny water, gives the possibility that if there's life on Mars, that we have a way to describe how it might survive, and that we are now at a point technologically, with over 50 years of successful space flight, that we have the capability to go there, ask this question of is there life on Mars, and answer it. This is, to me, the most exciting thing, is now that question is not an abstract scientific question. It's a concrete one that we can answer.
Michael?
Yeah, I would just like to add sort of a sensibility about how much we don't know. We have only one example of life, and that's us. This is it, on planet Earth. We don't know how it started. And so one of the things that we found at Mars is we know that Mars could have supported life, at least what we know about life. But we don't know how life started here, so we don't know if it's possible for life to have started on Mars. And so that's a huge question that needs further exploration. And it's only through that exploration that we're going to narrow the possibilities down and maybe get actually a direct answer.
Does that question...
I'm just going to expand a little bit on that. Now that we know what we're looking for, with HiRISE, we can begin a better search. We can begin to be more methodical. We can look and see if we can determine if there is some sort of aquifer network that may be supplying these. We don't know that. There are other theories, other ideas, but that is actually the next step. How much water that, when it left the planet, went into the soil, went underground. And that, as we said, is also a resource for human exploration for us. So if there is indeed those kind of resources that we can begin to probe, we might be able to answer that question pretty quickly.
So that question probably knocks out half of the questions we're going to get today. Let me see if our scientists in France or Mary Beth, if you all want to chime in on that question. I will start with France. Alfred Aluji?
Well, I would just say that I think the possibility of life in the interior of Mars has always been very high. There's certainly water somewhere in the crust of Mars. And Mars has received meteorites from Earth. It's been contaminated by Earth, rocks, and we know that microbes can survive that trip. So it's very likely, I think, that there's life somewhere in the crust of Mars, microbes. But where is it? How accessible is it? It's very difficult now. Maybe there's something we can find close to the surface, and that's what's exciting. But to me, the chances of there being life in the subsurface of Mars has always been very high.
Okay, just a reminder to our many social media folks, send in your questions at #AskNASA, and we're going to continue here at headquarters before we go to the phone lines, and we have this lady here, then here. Give your name and affiliation, please.
Hi, Anna Wilding, Herald de Paris newspaper. We publish in English and French. How will today's announcements affect your time frame for going to NASA and the possibility of coming back? And is any budget allocated towards cultural resources, finding any sign of cultural resources on NASA? I know you're looking at the water, but what about potential habitats or anything like that as well? Is there a budget?
Well, we do have a Mars budget for future scientific exploration, and in fact we have a number of exciting missions that are queued up, both NASA-led and also European Space Agency-led with the partnership with Russia. And so we have the InSight lander, which is going to launch next year, and will tell us about the interior of Mars. It's the first time we're going to look into Mars by putting a seismometer, sort of an earthquake sensor, and a heat flow experiment to tell us about the interior of Mars. And so that's very exciting and is linked to these broader questions. The European Space Agency with Russia is launching a mission called ExoMars, also in 2016. And in 2018, they have a lander going down. And in partnership with NASA, we have an organic molecular analyzer. And they're going to have a deep drill that's going to drill under the surface, bring up materials, and analyze it to see if there's organic matter, meaning related to carbon compounds, but specifically ones that might have been created by life. So that's very exciting. And then in 2020 is our next big NASA rover following on Curiosity that will actually collect samples so that eventually we can bring them back to Earth, put them in our best analytical instruments, and see if we see any signs of ancient or conditions that would tell us that there's life on Mars. That's just the beginning. That's just in the next 5 years. Beyond that, we have lots of plans as part of our journey to Mars that include developing the Space Launch System, a big rocket that will better in the future be able to get payloads to Mars and perhaps a round-trip mission. And we're still sketching out what that looks like. The future is always more fuzzy than the current, but certainly these exciting results only encourage us for the future of Mars exploration.
We also shouldn't discount what we currently have as assets that are there. They're actually relatively healthy. The Mars Reconnaissance Orbiter is doing a fabulous job. It's got high-resolution imaging, and as we talked about, the mineralogy from CRISM that it's been doing. When you look at, even though it's been there nearly 9 years, it's only really mapped about 3 or 4% in high resolution of Mars. There's so much more that we need to do to really look and understand this kind of network all over the place. And with that, it'll enable us then to narrow down on some better places or more accessible places where we can get access to these kind of regions to really thoroughly examine. Curiosity is also in a nice location. It's in Mount Sharp. It's doing great. There's potentially some dark streaks that are on Mount Sharp. We don't know much about those. We don't know if they're reoccurring slope lineae. There's a possibility that more observations will eliminate those or give us more data that could tell us that they also could be RSLs that we might be able to visit. So there's some really exciting things just coming up, even with our current assets.
One more question, and then we go to the phone line. Sir?
David Curley from ABC News. John, let's talk about astronauts. This really is a breakthrough for human travel to Mars. You could now purify the water, create oxygen. This makes it much easier, doesn't it?
Well, I think all of the scientific discoveries that we're making on the surface of Mars, at Curiosity at Gale Crater, these observations from Mars Reconnaissance Orbiter are giving us a much better view that Mars has resources that are useful to future travelers. When you have water, what's water? Hydrogen and oxygen. That's what we make rocket fuel out of. Perchlorates. The space shuttle, the solid rocket boosters are aluminum perchlorate. In principle, you could make solid rocket fuel. And as we've talked about, perchlorates are ubiquitous around Mars. But the water really is crucial because we need water to drink, oxygen to breathe. We have carbon dioxide, also oxygen. So there are plenty of resources on Mars, even nitrogen in the atmosphere, which we don't usually think about because for us it's relatively inert. But it's crucial for life, both if life exists on Mars, but also, once we get there, we're going to need nitrogen for a variety of purposes. So I think, Mars is looking more and more that, it's a potential habitat for extant life on Mars that could be, as you heard, from transfer from Earth one way or the other. Some people say we're Martians. It could go either way. But the exciting thing is that I think we will send humans in the near future to Mars. There'll be scientists looking for signs of life, and also to be able to live on the surface, and the resources are there.
I think it's important to realize that NASA's approach to exploration is not Star Trek. It's not go where no man has gone before, as they say. It's really a very methodical approach for which we learn everything about the environment that we're going to subject humans to that we possibly can. And that's why our rigorous scientific program is really the pioneers that are making steady discoveries. And I anticipate continuing to do that for many, many years before humans even get into the vicinity of Mars. We'll make rapid progress in these areas. That does indeed help us understand the parameters and design better missions, leverage and utilize the resources that are available, and even make those kind of trips more feasible in the future than ever before.
In fact, I'll be very specific. On our Mars 2020 lander, we have an experiment that's not a classical science experiment. In fact, it's a in situ resource utilization experiment. So you may hear that. We love our acronyms, ISRU. But it's a small apparatus that's going to take in Martian atmosphere, mostly carbon dioxide, and extract the oxygen. And that's its function. We know we can do that on Earth, but we're going to demonstrate it on Mars. And that's part of our combination of human space flight, space technology, and science all in one.
Now, in addition to that, on 2020 is underneath the rover is a radar. Actually, it's from Norway. They're building it, the Norwegian Space Agency. And this is a radar that will send radio waves through the ground, return reflections, will tell us what that strata is like, and it might be able to uncover aquifers that are close to the surface. It could tell us how important experiments like that are for humans to be able to take and go to Mars. And in fact, the MOXIE instrument, which is great, we're going to operate that all times during the day. There's huge temperature and pressure swings on Mars. So what is it like? What's the efficiency of extracting the oxygen under various extremes, not only during the day, but all throughout a season? So these are huge steps for us to be able to plan the right resources to support humans in the future.